For every action, there is an equal and opposite reaction. Newton's third law is often quoted, but little understood. It is tangled up with the other two laws, in that the laws all act at the same time in all objects. We separate out these laws so that we can better understand them. Imagine that you are stood on a floor. Now, I want you to think about jumping up into the air. What are the forces involved in this situation? It is quite difficult to envisage. In all examples of forces, it is useful to draw yourselves a diagram. You can be represented as a box that will be subject to forces. Prior to the jump, you are stationary, so the forces acting on you are equal and you have no velocity. It is possible to have a similar situation where the forces acting on you are zero and you do have velocity, but this only happens in space, or a vacuum on Earth, without frictional forces to slow you down. The forces acting on your body are in equilibrium. We have come across equilibrium before. It means that the forces are acting in an equal but opposite way upon you. The force of gravity downwards is equal in magnitude but opposite in direction to the reaction force of the floor upwards. In space, you would have no force on you, so the overall forces would be zero. Here, we see the first example of a pair of forces, gravity and reaction. If you were to increase your mass, then the force of gravity would pull on you more. The floor would in turn increase its reactionary force upon you, making you remain in equilibrium and stationary. You can keep on increasing your mass, and the reaction force will keep on increasing until you reach a critical point in the structural integrity of the floor, and the force you are applying to it is greater than the forces it can withstand. The floor then breaks. In this situation, you'll have removed the reaction force. The force will no longer be balanced, and you'll accelerate downwards. When you strike the next floor below the one you have broken, you are held. It is a stronger floor. However, the journey from breaking the floor above to striking it and resting on the floor below contains large amounts of pairs of forces which need to be described and better understood through Newton's third law. When you add masses to yourself, you are creating an increased downward force. This in turn generates an increased upward force. The action force, your increased mass, generate an equal and opposite force, the reaction force of the floor upon you. That small increase in mass led to an increase in weight. This caused an increase in the reaction force against that weight. When the floor gave way, there was an imbalance of forces leading to acceleration. This acceleration in turn generated a force as per Newton's second law, which changed your state of motion. It made you move, accelerate, as per Newton's first law. The floor giving way was a reaction to the additional force you applied to an increased mass. The additional force and its consequent motion were equalled by the floor disintegrating and chunks flying around the room. When you struck the floor below, you applied a massive force to this floor equal to your weight plus the force generated from changing your mass's velocity from moving to stationary. In order to hold the floor had to equal the force due to your weight plus the force needed to stop you from moving. Once this force was balanced, it became zero, as you were no longer moving and the forces became weight and reaction force once again. This is the same reason why a sledgehammer works. If you apply a sledgehammer's weight to a rock, it does nothing, because it's just the weight against the reaction force. However, if you swing this sledgehammer and apply the sledgehammer at a greater velocity to the rock may well break, because you have applied a greater force than just the gravitational force alone. Let's take motion in the other direction. Instead of falling through the floor, you are now going to leap into the air. In order to do this, you need to generate an acceleration, so that you can generate a force greater than the force of gravity attracting you to the centre of the Earth. It is here that you realise just how weak the force of gravity is. The entire mass of the planet is pulling you towards the ground. However, you can easily generate enough force to overcome this and jump. In our force diagram, we still have the weight and reaction forces, but now you generate a new force with your legs. In order for you to jump off the ground, it has to be greater than the force of gravity for an instant. You apply this force downwards. It is impossible for you to apply this force upwards, as there is nothing for you to hold. You have pushed down with your feet on the ground. This has generated a reaction force from the floor. It is this force that allows you to rise up into the air. You have pushed down on the floor, and it in turn has pushed back on you. The force that you push down is equal to the force that is pushed back upon you. If this force is great enough, then you can overcome the force of gravity pulling you towards the floor, and therefore jump into the air. Once you are in the air, there is nothing more to generate. There is no force against you, and so you fall back to the floor under gravity. What happens if we take gravity out of the situation?